So instead of, like on this square, as you got more positive, you kind of just like skyrocket it up. On the square root, as you get more positive, you increase more and more and more slowly. And that can be kind of evidenced by thinking of it backwards. Like if you're plotting whenever y equals 2, or let's start from the beginning. At y equals 0, x equals 0. Y equals 1, x equals 1. So that's like a whole increase of 1 in the y-axis. Whenever y is 2, x would have to be 4 to satisfy this. So you would go up 1, and you would go horizontally by 3. So it would be like a much lower slope. If you were to go to the next value, x equals 9, or whenever y is equal to 3, x would be 9. So again, you'd have a smaller slope, and you would just have a smaller and smaller and smaller slope, still increasing, but just more and more and more slowly over the course of the line. And the final function type is kind of funky looking. It's cubic. It's actually pretty similar to the quadratic function, except the negative values actually go faster and faster and faster into the negative y region. And the reason that is a cube is the same thing as a square, except instead of multiplying a number by itself twice, you multiply the number by itself 3 times. So you have a negative value, like y equals negative 1 to the third. That's the same thing as negative 1 times negative 1 times negative 1. So you multiply those first two together, you get 1, but then you have to multiply it by negative 1 again, so you end up with a negative value. So again, it's similar to the quadratic function, except as you go negative, your cubes are still negative y values rather than flipping to positive y values. So instead of sort of the, I lost my mouse, here we go. Instead of sort of the U shape that we saw before, you have your right side of your U going up and the left side of your U going down. So that's the primary difference, is quadratic would look like this, and cubic, you would have it quadratic on the right side, but then going the opposite way on the negative side. Still U-shaped, but just going downward faster and faster and faster. So that's a really quick introduction to what parent functions are. It is basically the just no slopes, no y-intercepts, anything like that on there. It's just a bare bones common type of function that you might see in mathematics. Again, you've mostly covered linear so far, but all of these other functions are things that you can and will see. So does that make sense? Clear as mud, right? Did I go too fast? Was there anything that didn't make sense?
No, it was fine. It was just that what's like, how would you do absolute value?
Okay, so absolute value, yeah, I'll just do that one again. You just have to know what the absolute value means and what it is. I'm trying to think of like, I mean, really the best way to explain it is this operation, these two lines on the number. What this means is to flip a negative number to positive. So I'm gonna like write out a table again here. So I'm gonna do X and Y and X and Y. So I'm gonna do two separate tables, and both of these have the same function, where Y is the absolute value of X. So what the absolute value of a number is, regardless of whether it's positive or negative, is just its positive whole number. So to explain what I mean by that, like if we were going to take the absolute value of 1, our Y value would be 1. If we took the absolute value of 2, our value would just be 2. And if we took the absolute value of 3, our value would just be 3. Same thing happens with the negative numbers, where if we take the absolute value of -1, our Y value is 1. If we take the absolute value of -2, our Y value is 2. And if we take the absolute value of -3, our value is 3. So I'm having a hard time kind of like describing it with words, but that's all the absolute value is it's just taking a number, whether it's positive or negative, and writing it as the equivalent positive number. So absolute value of any positive number is just the number, and absolute value of any negative number is just the positive of that same number. So what happens whenever we graph that out? It's the same thing whenever you're positive as y equals x, because the absolute value of a positive number is just itself. So it's just like your linear function. So your absolute value of 1 is 1, your absolute value of 2 is 2, onward that way. So in this positive quadrant, the absolute value function looks the same as your linear function. Where it changes is whenever you go into your negative x values. So if you remember, if you're looking at like a linear equation, this line goes down. It's like whenever x is -1, y is -1, x is -2, y is -2. It goes down this way. But what's different is we're doing the absolute value. So like we just showed in the number tables to the left, whenever x is -1, y is 1. It actually keeps going up rather than down. So x is -2, y is 2. X is -3, y is 3. And instead of drawing a line down that way, we draw the line up this way. Because it's basically, with the absolute value, it's transposing or it's flipping this whole negative section over the x-axis, because it's turning all the negative values positive. So you put the negative x values into the function, and you get a positive y value as your answer. And that's how your plot ends up looking. Does that make more sense?
Yeah, it does.
Yeah, so kind of the thing is it's just understanding what the absolute value is. And it is hard to like describe with words, but like whenever you understand that all you're doing is just turning the number positive, it's really easy. So that's what that function looks like. So hello, Terry. I see that you joined us. Sorry, I just noticed that you came in. Right now, we are, for Anastasia's request, we are talking about parent functions and transformations of said functions. I might have just gotten a chat. I'm not sure.
That was me. I was typing as you
acknowledged. Yeah. So I'm just saying, hey, Terry, we're working on this. If you have any other topics outside of this that you're interested in, we can pivot and cover that. Oh, I hope your test went well. What did you get tested over? Did it go well? I'll let you type that out while I get the next section ready. I don't know yet. I'll bet it went well. I hope it went well. Was it some of that, what was it that we did last week or the week before? Was it like discounts and pricing and sale price and things like that? Simple interest and sale price, yeah. Well, good. Good luck. I guess you already took it, but retroactively, good luck on your test. I hope it went well, and that's really important stuff, and that's really good to know in your life. So, yeah, I hope it went well for you. All right. Now that we've covered what the heck parent functions are, we're going to get into kind of the meat of what I think you were asking me about before, is transformations of said functions. So we have all the parent functions down here. Instead of y, you just say f of x for function notation. So y equals x for the linear, y equals x squared for the quadratic, x cubed for the cubic, just depending on whichever parent function you're working on. Sorry, I just got an email, so I was distracted. So these are transformations that you can apply to said functions. Oh, can you see Terry? Let me see. Is this too small to read, Anastasia? I'll try it because I know he just came in, so he might need to be looking at like the parent functions part too. So I'm gonna move that. Oops. Maybe I can't move that. I'm gonna move that here. I'm gonna move the graph. I'm gonna shrink this graph and move it over here. I'm gonna make this as big as I can. I can see all of that. I don't know if y'all can see all of that. If you can't, or Terry, if you need me to go back and zoom in on these parent functions and go over that, or if it's like too small, let me know. I'll keep an eye out for that on the chat. There we go. Make this pointer a little bit bigger. So transformation rules for functions. Yeah, you can just watch Terry. That's fine. I'll go ahead and zoom in over here then. You can just do whatever you want, whatever helps you learn the best. Hi, Eliza.
Sorry, I got disconnected.
You're fine. It happens. It's probably pretty cold up there, right?
Oh, yeah.
Eliza's in Chicago, if y'all don't know.
Yeah, I'm in Chicago.
So, all right, let's start covering transformation rules for functions. So I kind of just pulled this table off of online. It's a really good summary of these transformation rules. So first, we're going to have vertical translations. So f of x plus or minus some number. They call it d. I guess that's an easy enough variable. And what that does is this d is going to translate your function up or down. So let's make sense of that. Let's say f of x is x. Let's use our linear function first. So if we remember, our linear function was just like this. And hopefully I'm drawing it close to correctly. So that is f of x equals x. What we could do is we could vertically translate this 5 places. So all that would mean is it would be the same parent function, except we would start from here. So this line would be f of x plus 5 equals to x with our functional notation. We could also translate it down 5 places. So what we would do is we would have our same linear function. I'm just going to kind of draw it down here. This would be f of x minus 5 equals x. So like what this transformation of the function would be is it is just taking the same parent function that we covered before and translating it up or down depending on what you add to it. We could do the same thing with the quadratic function or any of the others, but I'm just going to do the quadratic function. But you could do it with any of these. So like our quadratic function, if we remember before, it was kind of U-shaped because all the numbers are squared. So if we transform this, we could transform this up 5 places. So what that would mean is we would have our same U-shape, except we would start at 5. This would be f of x plus 5 equals x squared. Or we could translate down 8 places. For f of x minus 8 equals x squared. So how I got that was I just took our basic quadratic function and I transposed it up, or I translated it down. So that's kind of the first 2 transformation rules. All that is just shifting the function on the vertical axis. So we can also shift it on the horizontal axis by doing pretty much the same thing, except we have to add the variable within the function. So we would say f of x plus minus c. So this is kind of one takeaway of this is whenever you're just doing a translation of a function with a whole number, if you add or subtract that whole number outside of the function, then it's a vertical translation. If you add or subtract that number inside of the function, then it's a horizontal translation. So I'm going to draw another graph. I'm going to use the quadratic function again. So our basic quadratic function, like we had before, I'm not going to write out the function again, but I'll just draw it for reference. Looks something like this. So let's say that we wanted to translate it to the right 8 places. So it would be the same thing, except we would start at 8 rather than 0. And then we would draw out our same parent function. And this would be written as f of x plus 8 equals x squared. Similarly, we could translate it to the left. 8 places, or however many places that we wanted. And it would be written f of x minus 8 equals our x squared. So that's vertical translations and horizontal translations. It's simply shifting the function up, down, left, right. And remember, if you're adding or subtracting the amount that you shift by outside of the parentheses on the function notation, that's a vertical shift. Inside the parentheses, that's a horizontal shift. So now we're going to look at reflections. Reflections over the x-axis and reflections over the y-axis.
Hi, Esther.
Hi, Esther. So I'm going to do reflections, and then I'm going to change gears because it's probably, y'all probably haven't done compressions and stretches yet. I just got a email or a message from Lillian for a topic for Terry.
Yeah, I don't think Terry has any topics, but if you do, Terry, just feel free to message them in the chat.
Okay, yeah, so it looks like we're live on YouTube. I see myself now. So Terry, let us know if you have a topic that you want us to cover. We'll have to switch gears to that pretty quick. We have 14 minutes left in the lesson. Send it in the chat or speak up or anything like that. And in the meantime, I'm going to keep walking through transformation rules for functions.
Yeah, I had the YouTube open, but we haven't got any comments or anything.
Gotcha. It looks like we came on about 6 minutes ago, so they probably saw me just in time going over vertical and horizontal translations. So I'm going to keep going.
Hello.
Hi, Esther. So now we're going to be looking at reflections. Looks like that graph wants to
What's
stay
that?
there. I am about to show you. So we're going to start with our base function again. We're just going to do the quadratic function because I think that one's a good representative. So this is f of x is equal to x squared. So a reflection is going to be just taking this parent function and exactly what it sounds like a mirror, reflecting it over the y-axis or reflecting it over the x-axis. So if we want to reflect it over the x-axis, we would just do the negative version of that function. So let me find my pointer. So how that makes sense is it's just the same function, except it's the negative every answer. What was that,
I have
Esther?
a question.
Yeah, what's up?
What does the green arrow mean?
The arrow?
Yeah.
Pretty much that it goes on and on and on forever. So whenever we draw, these are functions. It's just like mathematical ways, mathematical notation for graphing the results of equations. You put a number in as your x value. You get an answer for your y value. And these graphs are, you can only go so far drawing it out, but they actually go for forever. So we show these arrows just to say that it keeps going on and on and on. We quit drawing at this boundary, but just know to the viewer or whoever's looking, this function is going to keep on going. It goes to infinity. So we could never draw that far. So that's what those arrows are showing, is it's just
the
going
one
on
that's
and on.
in the precipitance, the green arrow that's going up.
That's the that's the share your screen button. You can't
I don't
share.
know about that.
Yeah, it's the share your screen button. You can't share right now because Matt is going over a lesson.
So I'm going to get back on track here. We're going to do a reflection. So we're going to draw out negative f of x equals x squared. So this is going to be a reflection. over the x-axis. So it's going to be our same U shape as our quadratic parent function, except it's going to be pointed downward and go downward pretty much forever. I'm going to do a different function for the reflection over the y-axis because the quadratic function is just the same thing. It doesn't really work out that well for us. So I'm going to do the linear function. So our linear function is just a straight line like this. And a reflection over the x-axis would mean taking the y value at every point at the same x value and essentially putting it in the opposite place. So this is f of x equals x. F of negative x would be drawn like this. So it's every answer to our function, but just flipped over the x-axis. So again, to summarize for the translations that we've seen so far, you have vertical translations, up or down, which is whenever you add or subtract a number from your function. You have horizontal translations to the left or to the right, which is whenever you add a number or subtract a number, but you do it within the function. So instead of like f of x plus 8, it's f of x plus 8. Or instead of f of x minus 8, it's f of x minus 8, if that makes sense. And then we also covered the reflections over the x-axis and y-axis. So,
I'm co-host.
I think I showed all of that. I might find. Alrighty. I guess Terry doesn't have another topic. Should I go ahead and go into stretches and compressions? That's a little bit harder to show, but I can try to show it. I'm going to erase all this and show it down here. That's okay. I'll just clear off one of the graphs that I have.
I don't understand this thing.
Yeah, this is a little bit beyond third grade, Esther, so you haven't seen a lot of this kind of stuff yet. Sorry, technical difficulties, but I finally managed to make y'all the graph. So I'm going to stretch and compress the quadratic
I
function.
can stay.
So we'll start again with kind of like our basic quadratic function. Looks like this, our U shape. So what we've done so far is we've bumped things up and down, left and right, reflected it over the x-axis and the y-axis. Now what we're going to do is we're actually going to bend or compress the function. So we'll write this as like a f of x equals x squared, kind of like that they have it up here. So like, let's say that a is a number greater than 1. As your number gets higher and higher, what you would do is you would essentially shrink the area of your function. So like this would be your normal quadratic. and this would be with some number, ax squared, and then you would shrink it further with a higher a. So as you get larger and larger and larger, your function would stretch, or essentially go in the vertical direction faster and faster and faster. So a horizontal compression is kind of the opposite. It gets fatter instead of skinnier and goes up higher. So f of b x equals x squared. As our b values got bigger and bigger, you would have a function like this. Similar U shape, except wider than your x squared. So this would be your f of bx. And as b got bigger and bigger and bigger, it would get wider and wider and wider. So that's sort of what that last transformation rule is for your function. I guess kind of in summary of everything that we've done, we went over parent functions, which are kind of the most basic bare bones versions of all kinds of functions that you might have to graph. Linear is a straight line, quadratic is sort of a U shape, absolute value is a V shape, on and on. I won't go over those again. And then we can transform the functions. So you can take your basic straight line or your U shape or whatever parent function you have, and using these rules, you can translate it up, you can translate it down, to the left, to the right.
To 126.
You can reflect it over either your x-axis or your y-axis. And then kind of this last part, you can multiply it by a factor that it's a little convoluted here, but you can either stretch out your function, make it go vertical faster, or you can stretch it out in the horizontal direction, make it go wider on the x-axis faster. So does that kind of cover what you were asking about, Anastasia? Does that make any more sense? I think you just started this yesterday, so you're probably just getting introduced to these transformation rules, but that's sort of the concept of what your parent functions are and what your transformation rules are. Do you have any questions about any of that, or does anyone have any questions about any of the stuff that I covered? I know it's kind of hard to represent, especially with the stretches and the compressions. But if anyone has any questions about that, go ahead and let me know.
Well, like the hardest thing for me to do is like how to identify if it's like a relation or like compression or like a translation.
Yeah, I see what you're saying. It's probably, you're probably alluding to these rules right here. So I'm going to think about how to explain that real quick and see if I can explain that to you well. I think kind of the best thing to do is look at how this change to the coordinate point is written out. It's actually kind of more clearly explained here. And imagine what happens if you plug in numbers for a at a certain point. So like to stretch your function, whenever you have it on the outside, a f of x. Is what that ends up looking like is your coordinate goes from just x to y, it's x to a y. So whatever your value of a is multiplied by your y value. So you can imagine that if you have like a is 2, a is 3, a is 4, any number greater than 1, then it's going to stretch your function. Because instead, like let's say x and y is 1 and 1, now it's 1 and 2. If a equals 2, like if you were to plug in numbers. So let's do this. I have just a minute, but I'm going to do this quick. I'm going to do a equals 2 and a equals 1/2. So our base function is x and y. We're going to do 0, 1, 2. 0, 1, 2. So whenever a equals 2, our y would be 0, 2, 4. Or if like we had a line, if our original line looked like this, whenever a is 2, our slope would go up. So we would stretch our function. Similarly, if a is 1/2, y would be 0, 1/2, 1. So we would actually compress our function in the vertical direction. It would, by compress, I mean it'll go up less fast. The opposite holds true whenever it's inside here. It's how you modify the x value. So you'll have a horizontal compression whenever b is anything greater than 1. And you'll stretch it in the horizontal function whenever b is anything between 0 and 1. So I'm out of time, or I would write it out, but I think kind of the best way to visualize it is to look at how the function notation for the stretches and the compressions looks and how it modifies your change to your coordinate point. And then I would write out your linear equation, or like your linear points like I did here, where x is 0, y is 0, x1, y1, x2, y2, with your linear equation, f of x equals x. And then try plugging in different numbers for your a and your b and seeing what happens to your graph. And so you'll kind of pick up on trends of how your graph changes and how the look changes. So I'm out of time. Thank you, everybody, for attending. Hopefully that was helpful and that was a good introduction. And y'all learned some stuff.
Yeah.
So I'm out next week. Go ahead.
I was just going to say, it's easiest to remember you're translating like based on this graph or based on this table, like if it's plus or minus either the x or the y, you're going to move up or down, right? And then if you're reflecting, it's going to be multiplied by a negative number, either the x or the y. And then stretch or compression, that's multiplied by any number for either the x or the y. So that's kind or dividing. So I guess that's, you just kind of have to memorize that and then use whatever they give you.
Oh, that's a good way to think of it. Yeah, like you write out your points, like she's saying. And
I gotta
then
go.
with the y value, you modify the y value with whatever translation you're doing to your function. Or you modify the x value depending on if it's inside or outside of the parentheses. And then regraph it. That's a good way to represent it too. Is that what you were kind of saying?
Yeah. If you're still going over this next week, Anastasia, we could go over some more problems, but yeah. I think that was a good intro. It's kind of hard to shove that all into one lecture.
Yeah. Yeah, but I have exceeded my time, so I'm gonna go ahead and hop off here. And again, she's here next week. I'm not, so y'all have fun next week, and I will see y'all in mid-November-ish whenever I'm back. Study hard and good luck, guys.
Bye, guys.
Goodbye.
Goodbye.
Let the staff sharing your screen.
Oh, am I? Thank you. Thank you.